Okay, before we jump into our whole day today, which is about exponential and logarithmic functions, I just want to remind you of the relationship between exponential and logarithmic. You guys were introduced to these back in Algebra 2 and then again in pre-calc, and being able to understand the relationship between them. There is a lot of algebra that goes behind the solving and the flipping back and forth between algebraic and logarithmic, but I just want to give you a quick reminder that if I were to have something of the format log base b of a equaling x, then I could rewrite that as an exponential function and how those are related to each other. And just remember that always the base of the log is the same as the base of your exponent when we rewrite them in their alternate form. So if it is log base b, the exponential that is related to this would be b raised to the x equals a. As I'm thinking about this in my head, this question up here is saying that this number is raised to something to give me this answer, right? That's logarithmic versus exponential. And we flip back and forth between those two formats when we are solving exponential and logarithmic, because it will allow us to access or solve for different parts of those equations, but remembering how or what the relationship is between those can be very important. Now, one of the things is you also will need to remember how to type it into your calculator, and knowing either how to correctly type a log base anything into your calculator or your change of base, which I will remind those that have the older operating systems on their calculators how to do their change of base. But I want you to go ahead and do these. The top two will require a calculator. They are ugly answers, round to 3 decimals. The bottom 3 we actually should be able to do without calculators, and those would be great examples of questions that would be expected of you to be able to answer on non-calculator forms of assessments. So I'll give you a second to look at those 5. All right. On this first one is just a very simple exponential equation. If I'm solving for an exponent, I want to utilize my logarithmic format on that, and then I could rewrite this in my logarithmic form. Log base, same base as my exponent, right? So log base 2 of 30 equals the exponent. And that is something a lot of our calculators can do, not all of them, but a lot of our calculators can do. Mine's under the math menu, like second option from the bottom says log base, and it allows me to type in something that has a base other than 10, which is your standard for log. If you do not, if you have an older operating system on your calculator, you have to remember your change of base formula. So this is for those who have the older operating system. Your change of base would be log of 30 divided by log of 2, and you can just then use log base 10, which is what every calculator, including like scientific calculators, can do. You don't need a graphing calculator to be able to do that. It does come out ugly, so we would round to our nearest 3 decimals, 4.907. Okay. On the second one, remember that you do need to get the exponential term by itself before flipping to logarithmic. So the first thing I would do on this one is subtract 5. And then flip to logarithmic. Log base, same base as my exponent, so log base 3 of 115 equals x minus 2. Log base 3 of 115 is 4.319. Add 2, 6.319. That all would require calculators. The bottom part does not. I like to think through the bottom part in terms of exponential because that's how my brain works a little bit better. So a lot of times you'll see that I rewrite these in exponential format, making it into equation. 5 raised to something gives me 125. 5 raised to something gives me 125, and it's easier for me to think through it in that format. And then I can see that 5 would need to be raised to the third to get 125. Okay. The next one, this is a couple of reminders. First of all, that if there is no number written as our base, that for logarithms, that it would be a base 10. And so this is saying that 10 is being raised to something, and it would give me 1. Okay, well, what would I need to raise 10 to give me 1? 0. Anytime anything's going to equal 1, it got raised to the 0 power. The last one is a couple of reminders. One of those is that if we see that ln, that's for natural log, and natural logs are log base e. It will never be written that way. You'll never see a base of e, because if it is a base of e, they just write it as ln. Okay? But if I again think through it exponentially, that it is a base of e down here, and that is saying that e is being raised to something, and I get e, right? And so this is a couple reminders. First of all, that it's a base e, but second is this. If I am raising something to an exponent and I get the exact same thing, what's that exponent? A 1. And that would go for any of them. So if I had like a log base 8 of 8, 8 raised to what gives me 8, and that would be 1. So if your base and this match, that is 1. Okay? Any questions on your log or exponential basics? All right, so now we're going to get into the calculus part of it, and that is, okay, well, if I have an exponential function, how do I find the derivative? We're going to see a couple up here, and then I'm going to talk about how they're all related at the end here, and by all related, I mean all the same thing. But it's a little tricky on us because we've never seen this before. The derivative of the function e to the x, remember e is just a number, e to the x. The derivative of e to the x is e to the x. The derivative of that function is exactly the same function, which is weird, I know. We rarely see something like an e to the plane x. Usually there's going to be like a function sitting up in this exponent. And that's where the second one is coming into play, is that if it is e raised to some function, more than just a plain letter x, that I start out with the original, e raised to whatever that was, but then chain rule. Follow it by the derivative of the exponent. So when we are looking at an exponential equation, the exponent is your insides, right? So we would apply chain rule to that. So that's exactly what we're looking at in this example. Y equals 2e to the 2x. Remember that if we've got, did I say 2? 3e to the 2x. If we've got a constant multiplier out front, remember it's just along for the ride. Okay, so nothing's going to change about that. We're going to multiply 3 by the derivative of our function. So to do the derivative of our exponential, it will look exactly as is to begin with, because the derivative of the outside function is just e to the x. So we would have 3e to the 2x. And I put 2x in green because that's the inside of our function. And it's not going to change when I do the derivative of the outside. Times the derivative of the inside function. So times the derivative of 2x, which would be 2. And I can multiply the 3 and the 2 together and get an answer of 6e to the 2x. Questions? Okay. Now, what if the base is any other number besides e? Well, it looks a little different, but we'll talk about how they're actually the same thing that we're looking at. If it's any other number, 2, 5, 7, any other number as a base raised to an x, we get the original, a to the x, but then you also follow it with times the natural log of the base. And if the exponent happens to be more than just the letter x, we apply chain rule. So derivative of the outside is the original, a to the exponent, times the natural log of the base, times the derivative of the exponent. I think it's nice to see them kind of split into those 4 different situations. However, they are all exactly the same rule, and that same rule is really this last one. How is this the same as what was going on up here? Well, when we do the derivative of the outside, it's just e to the x, and then it would be the natural log of the base. Well, the natural log of e is 1, which is why we don't see it up there. And then the same thing, the derivative of the exponent. If that exponent is just an x, it's 1, which is why we don't see that as well. So really, this is the rule. Can just be simplified a little bit if our base is e, because natural log of e is 1. Okay, so let's look at an example where our base is something other than e. Y equals 5 to the 3x minus 2. Exponential problem. Our exponent is a function more than just the letter x, so I know I'm going to be doing chain rule. Our format for this would be the original, so whatever it starts out as, 5 raised to the 3x minus 2. Times the natural log of the base times the derivative of the exponent, and the exponent being 3x minus 2, derivative would be 3. Okay, so then if we need to talk about what's appropriate algebra simplification here. Can I take this 3 right here and multiply that 5 and get a 15? Can I take this 3 right here and multiply that 5 and get a 15? No. That's inside a function. That's the base of that function. We can't change those things, right? So actually, there's really nothing. You could rearrange the order if you wanted to, but there's nothing that's going to change about those 3 terms that you see up there. Any questions about that? Okay, let's talk about when they're in the logarithmic form, and I'm supposed to take the derivative. Okay. Again, we'll see exactly like we just saw on the exponential page. They'll look like 4 different rules. It's really one rule. I might pay a little more attention to just the difference between natural log versus log base anything else. But if we've got just a plain old natural log of x, the derivative of that is 1 over the insides, 1 over x. Okay, well, if our insides is more than just the letter x, it's some function, natural log of some function, then it's chain rule. 1 over the insides times the derivative of the insides. So the example I have up there is exactly that. It's got an inside that's more than just an x, so we'll have to apply chain rule. The derivative of the outside function, the derivative of natural log, would be 1 over the insides. So this would start out as 1 over, and our insides are 3x squared, times the derivative of the inside, so times the derivative of 3x squared would be 6x. Okay. And that looks like it'll simplify here, which would be 2 over x. Questions? Okay. Similarly, if our base changes to something other than e, so now it's a log base anything else, the rule is almost the same. It's 1 over the insides times the natural log of the base. And up here, when we would have multiplied by the natural log of the base, that would have been the natural log of e, which is 1, which is why you don't see that in this rule up here. Same rule, though. 1 over the insides times the natural log of a. And again, if the insides are more than just the plain letter x, it becomes chain rule. 1 over the insides times the natural log of the base times the derivative of the insides. So overall, this is the actual rule for all logarithmic functions, right? We can just simplify it a little bit, especially when it's a natural log and our base is e. Looking at an example here, sorry, y equals log of x to the third. Find the derivative, so that is a chain rule. Outside function would be log base 10. The inside function would be x to the third. Remember, if it doesn't have a base, it's base 10, right? So this would be 1 over the insides, so we're here, 1 over the insides, which is x to the third, times the natural log of our base, and our base, although not written, is 10, times the derivative of the inside, which would be 3x squared. Okay, cleaning that up a little bit, we could simplify out an x squared from each of those, and we'd get 3 over x natural log of 10. Any questions for me? Now, didn't spend a lot of time talking about this, but there are rules that go along with logarithms of being able to rewrite them, move things around, condense, expand, all of that. Those still apply. So like we were talking about in our warm-up today, rewriting functions in equivalent forms, you can do that with logarithms as well before we do a derivative. That could maybe speed up our process or things like that. So always looking for that as well. All right, so just doing a couple practice problems here. Find the derivative if the function is y equals e to the x plus x squared. All right, moving ahead with this chapter, these two new rules are ones that you have to know these. These are not a read them out of my notes and be able to apply. These are a have to have memorized type of rules. So I would look at adding them to my pile of flashcards that I have for my trig derivatives or whatever it is, but we've got to practice these so that we know when I see an exponential, how do I attack that? Well, when it's an e to the x, we get the exact same thing to start with, which would be e to the x plus x squared. That's a chain rule problem because my derivative is more than just x. So now I take it times the derivative of the exponent, or the derivative of the inside, which would be 1 plus 2x. And that's just power rule and our our sum of terms there, so we can do the derivative of each one individually. Looking at how that would be written, a lot of times that would be distributed through, so we would get something, if I distribute that through to the 1 and the 2x, we would have e to the x plus x squared plus 2x e to the x plus x squared would be a common way to rewrite something like that. Questions? All right. Moving on. This one, at what point on the graph of the function y equals 2x minus 3 does the tangent line have a slope of 21? So a couple things I want you to get out of, again, the question itself. Always paying attention to what kind of answer am I supposed to be giving? Well, the very first couple words tells us that. At what point? So to answer that, I would answer a point, right? I would answer some x comma y. That's what the question is. At what point? And that point is going to be on our function, y equals 2 to the x minus 3. And then reword the last part. Does the tangent line have a slope of 21? What else could we say that as? The derivative. At what point does that function have a derivative that equals 21, right? Isn't that what that's saying? Okay, so that's exactly what I do, is I just set my derivative equal to 21. Find out where that's happening. What x value do I get in that equation when I solve for x? So job number 1, find my derivative. Okay, our function is an exponential. So our rule for exponential says we start with the original. That's not going to change. We get 2x, and if our base is something other than e, we also take it times the natural log of the base. So the derivative of 2x is 2x natural log of 2. The derivative of minus 3 is 0, so that's no longer there. And I want to know when this is 21. So I would set it equal to 21 and solve for x. And that's when we have to remember how to solve an exponential equation, which we kind of did at the beginning today. When I solve for an exponential equation, I need that exponential term to be by itself. Well, right now it's times the natural log of 2, so I would get that out of there by dividing by the natural log of 2. Whatever ugly number that is that my calculator is about to tell me. Okay, and again, we're now at that exponential stage, so I would flip to logarithmic. Log base, base of my exponent. Log base 2 of 30.297 equals the exponent. That's, again, something I can just type into my log base function on my calculator. Okay, so I get x equals 4.921. And again, we go back to the question. That's not answering the question. The question says at what point? Well, right now that's an x value, but there's an x in a point, right? We just figured out the x value of the point, 4.921 comma something. And if I want to know what that comma something is, I'm supposed to be finding this point that's on my function. Well, the x value is 4.921, so I put the x in there, plug it in, and it tells me what y equals, right? And I can put that as my y. So to find this, I plug in 4.921 and get another ugly number. $27.295. Questions? All right. Okay, this one is a little bit challenging and kind of a good way for us to talk about that. Sometimes there's not a direct path, and we just have to think about all the different things we know about things like slope. And this one talks about a line with a slope of m, passes through the origin, and is tangent to the graph of y equals natural log of x. What is the value of m? Okay, a line with the slope of m passes through the tangent, or passes through the origin, and is tangent to the line y equals the natural log of x. That's the graph of y equals natural log of x. Okay. So it's tangent here at this point. It's got a slope of m, goes through the origin, all these things I know about it, right? First of all, when I read a problem like this, I say, oh, It's tangent to my graph. Well, tangent I know goes with derivative, right? So my mind immediately goes to find the derivative of the function. So my function is natural log of x. So if I find the derivative of that, derivative of natural log of x is 1 over x. Okay? And they say that it has a slope of m. So this is our slope, right? So m is 1 over x. Doesn't really have value, is it? Because it's still got a variable in it. So I'm currently at an equation that has two variables in it. So that's kind of a dead end because there's nothing really else to do with that, is there? Okay. So then I think about, okay, well, I know some other stuff about this line. I know that it goes through the point 0, 0, and I know it hits the graph at this point. Well, the other idea behind slope is that if I know 2 points, I can put it into my slope equation, right? Maybe we can go that route. One of the points on my line is 0, 0, goes through the origin, right? It is tangent to my graph at that point. Well, that point's going to be some x value. And if it's some x value, when I plug x in here, I get natural log of x, right? So that would be a second point on this line. And the slope of that line, which we call m, would be my slope formula between those 2 points. Natural log of x minus 0 over x minus 0, or m equals the natural log of x over x, which is still not a value, is it? Okay. But now at this point, I've run into two equations that have two variables, yes? And that's what we need if I have two variables is a system, right? I've got a system of equations. I've got one equation over here, both of which have x and m in them. And I could do something like substitution, where I take what m equals, 1 over x, and plug it in for m in the other equation. So I can plug in 1 over x in for m here and get 1 over x equals the natural log of x over x. True? Okay, well, if 1 over x equals the natural log of x over x, then 1 equals the natural log of x, right? This is where we got to remember our logarithms. If 1 equals the natural log of x, what's x? E, right? Because it is this base raised to this number equals that. Well, this base is e, raised to the first is e, right? So x equals e. That's not our answer. Our answer is, what is the value of m? So we need to say m equals 1 over e. I can now plug that value. E is a value. I know it messes with our heads, right? Because e looks like another variable, doesn't it? But e is the number. It's just like it had followed through this problem and it was a 5. I now just told you that the slope is 1/5. It's not 1/5, it's 1 over e, but that's a value. There's your slope. Questions? That's an ugly one, right? Ugly one. All right. See how much more we can get done here. We might be able to get through everything. This next one's pretty quick. It says find dy dx if y equals log base a of a to the sine x. Okay, so a log base something other than e, right? Our rule says that it's going to be one over the insides, which would be a to the sine x, times the natural log of the base times the derivative of the insides. Well, the insides are a to the sine x, which is an exponential, right? So the derivative of the inside would be a to the sine x times the derivative of the exponent, which is cosine x. Oops, I forgot one, didn't I? Natural log of a. Sorry, derivative of the insides, a to the sine x natural log of the base, times the derivative of the exponent, which is cosine x. And pause there. All okay with that. Now cleaning this up, this is all in my numerator, so we'd have a to the sine x times natural log of a times cosine of x over a to the sine x times natural log of a. Okay, well, don't those cross off right there? And don't those cross off right there? And I'm left with cosine x. Okay. Questions? Now, I alluded to this earlier, but if you remember your log rules, we could try simplifying this first. And by simplifying it first, we could save ourselves quite a bit of work. One of the rules for logarithms, let me move down here, is I can take something like log base a of a to the sine x, and any exponent can slide out front. Remember that? Seeing that happen? And this can actually be sine of x times log base a of a. But if it's log base a of a, if it's the same base and number following, a raised to what gives me a? This becomes 1, right? So doesn't this original function, if I know my log rules, simplify down to y equals sine of x? And I'm supposed to do the derivative of that, which is just cosine x, which is what we got over here too, right? So two things out of this. First of all, always look to simplify if you can, because a lot of times that'll speed up our derivative process. But at the same time, it doesn't matter if you don't. You can get to the same answer as long as you follow all the steps correctly. You'll still get there, okay? Questions on that? So don't stress over, I don't remember my log rules. If you don't, you just have to do more work, and that's okay. You'll get there. All right. Last one we'll talk through very quickly. It says this: if f of x equals natural log of x minus 3, find the derivative of f of x. State the domain of the derivative. We'll talk about that in just a second. So the derivative of that, just continuing to practice, our log rule says it's going to be 1 over the insides. So 1 over. When it is a natural log, it would have been a natural log of e, which is not going to show up there, times the derivative of the inside. Well, the derivative of x minus 3 is 1, right? So that would be our derivative, 1 over x minus 3. Then let's talk about the second part of it. State the domain of f prime. When you are doing this, the domain of the original function is also going to follow us through the problem. So we have to keep in mind the domain of the original, but also the domain of the answer, or the domain of the derivative. So remember things like domain restrictions. When we have a fraction, that cannot equal 0, right? X minus 3 cannot equal 0, or x cannot equal 3. But if I look back at the beginning, do you guys remember what the domain restriction is that goes with logarithmic functions? You can't take the log of a negative, right? You cannot take the log of a negative number. So this, or 0, I should say, has to be greater than 0. X has to be greater than 3. So of those two things, x cannot equal 3 and x has to be greater than 3. This is the more restrictive of those two, right? Because this could be everything negative and positive, above and below 3, just as long as it's not 3. But this has to be just things that are greater than 3. This would be our domain for the derivative, because the domain of the derivative adopts the domain of the original function if it's more restrictive. Questions? All right. When we come back in our next lesson, we are just practicing these rules. So now it is practice, practice, practice time.